Um, we got a good show for you tonight. John Talbot's in the room, and he's gotten a presentation prepared for you. He's going to answer that question that we've seen all over the place: CCD-CMOS. Well, fact is, eventually it's going to be CMOS, and there are a number of us who have a lot invested in CCD, and we are going to have to migrate eventually. I mean, if we ever get older, we're going to have to migrate to CMOS. Well, he's going to be talking about that. He's going to be talking about particularly the ASI6200 and the QHY600 something. I forget exactly what. He knows all about that stuff, and he'll be telling us about it. But before we go and hear from John, I want to tell you about a few things. Let's go over to the website. I'll start by present my entire screen. And our website, as you know, www.theastroimagingchannel.org. If you go there right now, you will see a go to the Orion time tab above for your Orion submissions, and we'll get to that in a minute. But there's also a few other things I want to tell you about. One is the calendar. We got some cool things coming up. Jonathon's today. Tom Glenn is here. And hey, Tom, are you out there right now? Could you say a few things about what you're going to tell us about next week?
Yeah, sure. So I'm going to be talking about International Space Station transit imaging. So Alex invited me to give a talk about my Mars image, which some of you may have seen floating around on the internet with the ISS transiting Mars. So I am going to tell the story about that image and the planning and execution that went into it, but also I'm going to talk more generally about how you would go about imaging the space station transiting any object of interest, the sun, moon, and the planets. So it'll be sort of a general ISS transit imaging talk, and I'll have some animations and videos, and it should be a good time. And I'll also say, a lot of people have been talking about how CalSky, the website, is it folded up shop, unfortunately, in a tragic twist of fate after my image was published. But there are other methods, and basically transit imaging of planets goes on unperturbed. So I'll share the methods that I've used since CalSky folded up to continue imaging.
And if any of you have ever gone hunting the ISS, tried to image it, or I even once pulled it out in my Dob. I knew it was going to pass Vega at a certain point. So because of CalSky, and I put my I guess it was my 12.5-inch Dob on Vega and waited for that sucker to come by. And as soon as it came by, I started dragging my Dob along. It's really cool to try to catch the International Space Station, but you need to know a few things about it to do with that stuff. But it can be done. Anyway, Warren's coming a couple of weeks from now, and then we're going to take a couple of weeks off. Happy holidays, everybody. And Bob Buckheim's going to be telling us about scientific imaging. Kevin Francis got a really interesting story about his astroimaging journey. I haven't heard back from Chris yet, Chris Hendren, about what he's talking about, but we all know Chris. He's been around for a long time. In addition to knowing everything there is about the field of astroimaging and having sold lots of stuff in his life and taken a lot of pictures. He's Astro Image of the Day from APOD and all that other stuff. Steve Hummel is good. We hooked him up. Remember last week when we were hearing about all sprites and stuff? He's going to be telling us about taking sprites. Then we're going to take a break for the Super Bowl, and then Prima Lucha Lab will be here. And we're going to keep going on and on and on. We are desperate to get new people. We were scheduled all the way up to mid-February, and that's cool. But we need you to participate in this. Remember, this is a club. I mean, it's not officially a club or whatever it is, but it's supposed to be for astroimagers by astroimagers. Back when Adam started it, it was just like, hey, who wants to play? Who wants to and do this with us? And a few of us, we signed on back then. And since then, we've gathered other people around us. We need more of you to participate in this, not only as presenters, but possibly as people to help us put on the show, as people to help us get presenters. There's other things that need to be done besides what what you see us doing. So contact us using the contact page here. Tell us who you are, how to get a hold of you. Tell us how it is that you want to help. It can be presenting a full formal presentation. If you got a name for it, tell us what it is. We'll check you out a little bit. And if you sound like you know what you're doing, hey, fine. One thing I want to tell you though, there are some people who think that we know a whole lot more. And it's true that Eric and Terry and they've done some fantastic pictures and really, really, but you can't count me in that bunch. Okay. I'm just a good workaday average person who kind of knows how to organize stuff, not necessarily a good astro imager. So, and I can make decent presentations for the masses out there, and so can you. And we've had a few people come about once a month. We get one of you guys volunteers to come on in, like Ray did, and other people have done in the past. So please be part of that. Sign up here. But let's get back to the homepage where it says go to Orion Time tab, which is this tab right here. And in order to submit a file, you go to Orion Time tab here, and here are the rules. And you click here to submit a file. And I forgot, this is going to bring up Judy's. See, Judy's name is linked here. She's my name. She's my wife. And so every time I hit something that says go to email, Judy's email pops up. So I shouldn't have done that. But at any rate, you click on that and it will give you your email server, and you just put your links in there if it's a movie, or you submit a JPEG. Try to make it at least 1080 pixels on a size so that we can, so we can see something if we can do that. Okay. With that in mind, where else did I want to go? I wanted to go to here, and I gotta silence myself. There we go. Here is our program as it's going on right now, and you can see that people are already signing in, saying hi, saying hello. Don't forget, if you want to ask a question, try to put a question mark there. And I forget how to do it, but somebody will tell you over there. So that way we can spot the questions easier. Eric will pick them out, and hopefully he'll mention your name and say, hey, Fred or Molly or Jeff wants to know such and so and such and so. So, go ahead and ask your questions over there. You'll notice a few things here. There are places for you to subscribe. Where's that place to subscribe? I always lose that for some reason. We have tonight, what is it, 9,950 something. And as you all know, for Christmas, I want to get to 10,000. So if you are watching this and you are not yet subscribed, please go ahead and subscribe. And, there we go. There's places you can donate money and stuff like that. We're fine. We can use the money. That we do have some expenses that we have to pay for the website and things like that, but that's not why we're here. Anyway, sign on to Orion Time and sign up. Now back to, I'm going to stop sharing here. And YouTube example, volunteers. I think I've got my whole schedule, my whole agenda. So it's time for what you all came for. Let's hear from John Talbot. John, tell us what you're going to tell us about.
All right. Well, good evening. And thank you for allowing me to be here tonight to talk about CMOS cameras and CCD cameras and stuff like that. So first of all, let's see. Can you guys see my screen?
Yeah, you're good.
Okay.
And you're projecting just right.
Yeah, good. All right. Yeah. So thanks again for allowing me to talk about kind of my transition from CCD to CMOS. And it really hasn't been a total transition yet. I still have some CCD cameras, but the new camera is my main one at the moment. So I'm going to give you guys a little bit of an idea of how that's gone for me and what differences I've seen between the what I'm used to using, which is the CCD technology and the CMOS technology. So a little bit of background on me. So I spent about 34 years in the Air Force, and I flew through hurricanes and stuff. And I was a I had to deal with a lot of equipment and technology on the aircraft. And I was a project manager for this really cool instrument. And that made me learn a lot about how to test things. And so that kind of, moved me forward a little bit when it comes to testing cameras and characterizing stuff. And so hopefully, you'll see a little bit of that in this presentation. So it's called the ZWO ASI6200 and my transition from CCD to CMOS. But to really give you guys an idea, I have to go back to the beginning when I first started. So, I can't see you guys, but I'm sure if I raise my hand and say, hey, how many of you guys started with a scope like this? So in 1997, I started with a 60 millimeter refractor, and it was 600 power. And that was awesome, right? And I bought it because Hale-Bopp was in the sky, and I wanted to look at it with a telescope. I mean, I could look up and see it, but I wanted to be able to see it with a telescope. And I really quickly realized, hey, man, this is not the thing. A comet is not what you want to look at through a telescope, at least not a big one that's covering a good portion of the sky. So I spent time on the moons and the planets, and I could actually see the cloud belts on Jupiter with this little tiny scope, and it was, in the big scheme of things, it was okay for that, and I didn't really know what I should be seeing, so it was okay and it worked fine. And then the first real scope I had was a reflector, and it was another department store type telescope, but it had a computer. And I was really used to computers. So in May of 2000, I bought this 4-inch reflector, and I it had GoTo and all that cool stuff. And I could go around and see things. That was pretty amazing. And, this is coming from an individual that really had no experience prior to this with telescopes. So I spent a couple of years looking around the sky and seeing, faint fuzzies and stuff. And with this thing, I could see actually some faint galaxies from my backyard, which is kind of a suburban location. I've got about a Bortle 5 sky, I believe. So yeah, typical suburban sky, and it was kind of cool. So I eventually, started looking at magazines and stuff and saw all the cool pictures in magazines. And I really got the bug when my kids decided that they got too old to deal with mom and dad and they wanted to do their own thing. I needed something to do. So I eventually bought a LX200, which I'm sure many of us here probably have had that telescope. And I had a Olympus camera, which was actually a CCD camera, the C2040. And I took my first Astro image with that using eyepiece projection, and that's a picture of Saturn there. And I thought that was the coolest thing in the world, which drove, everything from that point forward. So I spent a couple of years using that, and I took a bunch of images of Jupiter and Saturn and stuff like that, and it worked okay. And this is just with with that LX200, an 8-inch reflector, Schmidt Castle grade, and it really got me hooked. And so after a while, I got to thinking, I saw these cameras on the market, and I thought, you know what, I'm going to talk to my wife. Let's see if we can buy a CCD camera. And that was a tough thing to do, but it worked out in the end. And my first camera was this Starlight Express MX7C, which was a camera that had a color chip. The thing with this camera, though, compared to the ones nowadays, this had a not a Bayer matrix, it had a CYMG matrix. And it was a really tough camera to understand how to balance color. It worked pretty good for the planets, but it did not work too good for deep sky stuff, at least not from my backyard. And that probably is because I had to deal with a lot of light pollution, and I really did not know what I was doing when it came to processing images at the time. So I read a lot of books, and off we went doing a little bit of research, but I was able to get a few good images from it. Here's M27, and you know, the color is not perfect by any means. The stars aren't perfect by any means, but it was the type of technology that kind of got me into this whole deal of astrophotography. So I upgraded in 2003 to a Starlight Express SXV-H9, which is a really nice camera. It was a mono camera, and I had to buy a filter wheel and all that stuff. And I finally learned that if you were going to be shooting from a sort of light polluted sky, it's probably best to use a mono camera. At least at that time it was, because I had a real hard time dealing with gradients and stuff. So this was my go-to camera for, I don't know, probably 4 or 5 years. And I was able to get some pretty decent images. Here's one of NGC 253. Some people call it I guess the silver dollar galaxy or something like that. But it's in the southern sky, and I had a 10-inch reflector at the time, which I still have. And this camera worked really nice with the scope. So I was able to get some really cool images once I started to learn, one, how to take them, two, how to process them, which were two totally different things. So as we moved along, in 2008, 2009, I acquired a STL 11000 35 millimeter format camera, mono, and I also purchased a QSI 583. And these were really wonderful cameras. They had fairly low read noise, pretty decent sensitivity. You know, the quantum efficiency of these was around 50-ish% as an average. And then in 2018, I added a 683, a QSI 683. So these were the cameras that I basically used up until this past July. And, you know, they were wonderful cameras. They took wonderful images. And as long as I spent enough time imaging from my home, like 20 to 25 hours worth of time, I could get images that were fairly deep, similar to what I could do at a dark site. And here's just a few examples. NGC 2403, I took with the 683 over on the left, and the dusty area around LDN 1495 with the 583, and 6914, which probably most of you are familiar with in Cygnus, with the 683. So these were wonderful cameras. They produced wonderful images. And as long as you learned how to use them and how to do it correctly and how to image long enough to reduce the noise, they were awesome. And I still have the QSI 583 and the STL 11 as we speak. I just haven't been using them too much right now. So here's an image I took with the STL 11000, and this was from my backyard with a scope that could handle a 35 millimeter chip of the NGC 1333 area with, I think this is VDB, it's either 13 or 16, and this is either 13 or 16, these two here. But this was a really dusty area. And this really opened my eyes to, hey, you know what? I am nowhere as close to a dark site, but I can still image dust. And, you know, it's all because of this technology, this wonderful technology that we had that was very, very sensitive to light and little tiny changes in light. So luckily, I was very, very fortunate that in April of 2019, I was able to acquire a 6-inch refractor. And it's a Stellarvue SXV 152. And it's a native f8 scope. So it's a little bit slower photographically than what I had been used to in the past. My reflector, my 10-inch reflector was f5 native and f3.8 with a reducer corrector on it. And then a lot of the other refractors I've used were around f6 or so. But this scope, you know, was my retirement scope. The scope I always wanted. I wanted a 6-inch refractor. I was able to acquire it, and so that's what I had to use. I can use this also at I should say at f6 also, which is 900 millimeters of focal length, but its native focal length is 1200 millimeters. But the neat thing about this scope is this is capable of handling a 35 millimeter format sensor. It's got a big enough image circle that's corrected with the field flattener and so forth that, yeah, it covers the chip just fine. So that got me thinking after I got this all set up and going. I originally had my QSI 683 on this scope, and I noticed that at f8, I really had to shoot for a long time. I mean, like 10 to 15 minute sub exposures were not out of the ordinary. And in 2019, last year, at the last Texas Star Party that was held, I went to, and that was the first light for this scope. And I noticed in the dark sky using my QSI camera that a lot of people don't tend to realize this, and I know a lot of you know this, but when you go to a darker sky, really your sub exposures get longer than what you would typically do at home to get to the same noise level, because the sky is darker and it takes longer to acquire those photons. So I noticed that at the Texas Star Party that year that, man, I really needed to shoot a long time, especially at f8. So I started thinking, about a new camera. And I know a lot of the younger generation of astrophotographers were using CMOS cameras. So I walked around the field and I talked to a whole bunch of them just to kind of get their idea of, what they liked about the cameras, what they didn't like about the cameras, how they thought they worked, and I found that most of them love the low read noise of the CMOS technology. And that's kind of a neat thing. They've come a long way in that sense. But you have to decide on the gain, and you have to decide on offset and things like that. And the more I thought about that, it's like, well, my CCD, I just plug it in, I start taking pictures, and I don't have to worry about any of that stuff. So the last big thing that they mentioned to me was a thing called amp glow, and I'm sure there's many of you out there that are familiar with that, and the problem that creates when it comes to calibrating your raw data that you collect. So after listening to these folks, talk about the cameras, especially the younger folks, on how they were able to deal with a lot of these issues. In the end, I kind of got the impression that they really love these cameras, and they're, these kids were smart. They knew how to calibrate the images. They knew how to take care of the amp glow. So I thought, you know what, maybe my next camera is going to be a CMOS camera. So I ended up in AIC in San Jose in 2019. And that happened to be when QHY unveiled their QHY 600. And it was going to be using the Sony IMX 455 chip, which was a 35 millimeter format chip. It was available in color or mono. They said that it had 0 amp glow and performance specs as good as any CCD camera that was out there. 50,000 electrons, full well capacity. I mean, that was pretty much what the STL 11000 had. My QSY only had probably, my QSI 583 and 683, I think it was around 29 to 30,000 electrons for the full well. So I was like, wow, that's pretty cool. In the QHY example, they have a different mode, which is called extended mode, allows the camera to go up to 80,000 electrons. But bin 2x2, here we're talking 320,000 electrons. I was like, oh my goodness, this thing is pretty neat. It's a back illuminated chip. It's 60 megapixels, 61 megapixels. And they were advertising 1 electron of read noise. And, I kind of had to take a step back and think about that. 1 electron of read noise. I'm dealing with CCD cameras that have 15 electrons of read noise on average. quantum efficiencies of around 40 to 50%. And here's a chip that's got 90% peak quantum efficiency. It's 16-bit, and it has really low dark current. So I was like blown away when I first saw this, and I sat there and I watched their presentation, and I was like, back of my mind was just spinning, thinking, boy, this could be really, really interesting. But, you know, advertisements are one thing, using a camera is a whole nother thing. So, you know, just because they say it's really good and it does this doesn't necessarily mean it's going to do it. So, you know, you really got to try that out. So at the same time, roughly in the fall of 2019, ZWO announced their ASI6200. And this used the same chip as the QHY600, you know, the IMX455. Same general specs. The price point was just a little bit better than the QHY, but it had a few less features. So that's understandable. And its availability was expected to be in early 2020. So, you know, it's using the same sensor, IMX455. It's full frame, 16-bit analog to digital converter, very low read noise of at least ZWO specs was 1.2 to 3.5 electrons, cooling delta of 35 degrees centigrade, and so forth. And it used USB 3. So once I saw this camera, I started going to a lot of the forums and just kind of seeing what people were starting to say about them. I read a lot of the stuff on Cloudy Nights about some of the early adopters or beta testers of the QHY600 and the 6200. And yeah, so once I saw what they you know, were able to do with the camera, I decided, you know what, I think this is going to be a good deal. And this is going to be a really good camera and a way to, you know, move into the new technology era and away from the 15 to 20-year-old CCD technology. Not that it was anything wrong with it. It was wonderful technology. It took great pictures. But it was a way to, you know, like all of us, a way to use something new. So I bit the bullet in May of this year, and I ordered the 6200 with the filter wheel. I got the mono version, and I guess I mentioned it does come in mono or color, but I got the mono version with a filter wheel and 50 millimeter round filters from Chroma. I got the LRGB, the sulfur, and the oxygen 3 filter, and I got 5 nanometer filters. And I already had a 5 nanometer Astro HA filter, so that rounded out the whole set of 7 filters. So the camera arrived in July, and I got it all set up. And here's a picture of showing you what it looks like inside my dome. I've got an 8-foot Explorer dome at home and a Paramount Mighty. So the mount's a little bit overloaded with this 6-inch refractor on it, but you know, it's pretty close to the max, but it works just fine. Here's kind of what the camera looks like in the back. And it's kind of interesting because they added 2 USB 2 ports on the back of the camera, which is probably common to the ASIs. But for me, you know, I wasn't familiar with them. So, but they work really well. I was able to hook my guide camera into one, and the USB 3 is up here, and then the power. So the other thing that was kind of interesting, moving from a CCD to a CMOS, was this being a USB 3 camera. I was hearing a lot of problems people were having about extending USB 3. So what I ended up doing is I acquired a Eagle 3 Pro computer, which is mounted up on the scope here. And, you know, I only have one little short cable run from the camera to the computer, instead of having to try to go through a hub and so forth. And I heard a lot of problems people were having with the new USB 3 cameras and hubs. So I figured I'd solve that problem right off the bat, and that worked really well. I've had no issues at all with the USB connections. Everything plugs right into the Eagle, and this could be a whole talk on itself, how the darn Eagle 3 works. But yeah, I haven't had any issue at all with the camera plugged into the computer. So, like any good testing guy, and I'm a meteorologist by trade, so a scientist by trade, and you're really the first thing you got to do is characterize your camera. You got to understand how it works, what you're dealing with when it comes to noise and so forth. So I did that. I did darks, bias frames, flats. I tested the linearity of the camera. And here's an example of a master bias. And this was done at gain 100. And I'll get into the gain a little bit later, but there's only really 2 gain settings for this camera. And this was bin 2x2. So if you look at this, I mean, it looks just like a bias frame from a CCD camera, and it looks just like a bias frame from my QSI. The STL camera is a little bit noisier than this, but there's no amp glow or anything. It's just a really clean bias frame. So that was a really good thing, and I was really happy to see this. So yeah, it's sort of acted just like what I was expecting to see. So I ended up characterizing the camera using a couple different gain settings. So for the ASI camera, there is gain 0 and gain 100. And the difference between the two is gain 0 is the base setting for the camera. Gain 100 is where the read noise really, really drops down. But you give up a few things. So let's see, let's go through some of these numbers here. So at gain 0, bin 1x1, -5 centigrade, the full well capacity of the camera came out to be 50,700 electrons, which was right near the specs that I saw in the advertisement. The dynamic range was quite a bit more than my QSI camera or the STL, almost 14,000 steps. The read noise is right in the ballpark, 3.6 electrons. And the dark current was really low. And remember, this is -5, 0.009 electrons per second. So really low dark current. Here it is at gain 0, but bin 2x2. What happens is the full well capacity went way up to 200,000 electrons, and the dynamic range really, really increased a lot, 27,000 steps. Well, look at the read noise. The read noise went up quite a bit, 7.3 electrons, but still not too bad. This is still well within the range of what most current CCD technology produces, around 7 electrons of read noise.
Hey, John.
Yes.
Could you possibly use the magnifying tool on your PowerPoint presenter to zoom in on some of those? They're hard to see on YouTube.
Okay. Where is that?
Well, I know a PowerPoint, if you like kind of hover over the bottom, it shows up, but
Yeah.
maybe it's different.
Yeah, this isn't PowerPoint. This is actually Keynote on a Mac, but yeah.
Okay, well, if you don't know where it's at, then don't worry about it.
Yeah, I don't. Sorry. So maybe this is a good time to stop. Are there any other questions out there before I continue on that anybody wants to ask, or it's out?
No, I'm watching over on YouTube. There's a lot of discussion about these cameras and about some that have and some that don't. But no questions yet, but I'm sure there will be, John.
Okay. All right. Well, great. Well, I'll just continue on.
Question? John,
So
Terry, do you have a question?
Yes, I do. With regard to binning, is that binning in software or is that a hardware binning, like on a CCD?
Yeah, great question. And I was going to get to this. I got some good slides to talk about this. This is software binning. It's not like a CCD that does hardware binning.
Okay, thank you.
Yeah. So, okay, so I moved on to the other gain setting, which is gain 100. And this is really where the read noise drops. Bin 1x1, -5 centigrade. noise here went down to 1.5 electrons, 1.57, really low. The dark current still pretty darn low, but look what happens to the full well capacity. It dropped quite a bit. And you may think, well, heck, it was 50,000 electrons. Now it's only 16,000 electrons. Well, on my QSI camera, the full well capacity was only 29,000 electrons to begin with. So this really isn't all that bad, but it does go way down. The dynamic range dropped a little bit, but still a whole heck of a lot higher than the CCD cameras I use. So what happens when I go up to 2x2 binning using gain 100, which is the low, I guess I should call that the low read noise gain. So the read noise now is up to 3.19 electrons. So it doubled. The dark current still really low, 0.02 electrons per second. And look at the full well capacity now at 2x2 at gain 100, up to 66,000 electrons. And the dynamic range has gone way up too. So here at gain 100 bin 2x2, I am really back to really, really high performance. So after I ran all these numbers, I started thinking, well, how am I going to, what gain setting am I going to use to shoot? I have no experience with this stuff. I just normally turn the camera on and go. So I did a bunch of test images, and I shot my first image with it at gain 0, and found that at gain 0, it acted a lot like a CCD, about the same exposure time, a little bit faster, but relatively sort of what I was expecting and what I was familiar with. So after I did all this stuff, I went to look at the linearity of the camera, and I'm here to tell you that this is a very linear camera. This is the data that I took, and I used the American Association of Variable Star Observers method of doing it, where basically I have a light source, and it's a constant light source, and I change my exposure time and then measure the ADU value. To be honest with you, this took me about 6 tries to do. This is a lot harder than than I thought it was going to be. And the reason being was that the light panel that I use, the Alnatac, which I've had forever to shoot my flats, it actually changes just a little bit. When you first turn it on and you set the light level to what you want, maybe you go back to it 5 minutes later, it's a little bit different. And 10 minutes later, maybe it's a little bit different again. So it skewed my numbers over, when I try to, I'd get some weird, I'd shoot for 10 or 20 or 30 seconds and I'd get values, and then I'd go to 50 seconds and then I'd get a value that kind of dropped down below the graph, and then another value that jumped up the other way. Well, in the end, it all had to do with the light panel and allowing it, enough time to warm up and to, stabilize. So once I did that, I got a very linear curve, and this really surprised me. I've got a friend who's a professional astronomer out in Hawaii. He works at the Keck telescope, and he was curious about the camera, and one of the things he asked me was, how linear is it? Because they were thinking about using this camera to do some research work. So in the end, it seems very linear, at least up through 50,000 ADU. At least that's what I've been able to come up with. Now I have noticed that QHY has shown some small little variations down in the very low levels with their cameras, and it may be in this one too, but I didn't really see it. So maybe, that particular version that they tested just did that. So I'm pretty happy. This acts just like sort of what I would expect with a CCD. And not all CCDs are perfectly linear either, but this I think is well within tolerances to do a lot of good variable star work and stuff like that, photometry and stuff like that. So anyways, moving on. Yeah, the tale of two flats. This is really interesting. So when I first took flats with this camera, you know, I'd set my light panel, I'd shoot for about 30,000 ADU, which is typical. And here's one over here on the right-hand side. And I noticed when I went to use 2x2 binning, I didn't have to change the light sensitivity at all. I mean, I didn't do anything. What I was used to seeing, and I'm sure all of you that use CCD cameras, is when you use 2x2 binning, which is hardware binning, you get a lot more sensitive camera, or the image is a lot brighter. And I didn't see that with this, so that was kind of, it floored me for a minute. I kind of thought, what is going on here? You know, if I shoot it 1x1 or 2x2, it's the same brightness. I don't change anything. Nothing's happening. Well, my friend Richard Wright, who gave a wonderful presentation on kind of where we were in the world of CMOS back a few months ago. I got with him a few weeks ago and I said, Richard, I said, this is kind of what I'm seeing. And he said, you know what, I'm going to email the engineer at ZWO. We'll finally get the answer. And I had a hunch of what was going on. There's two ways to bid in software. One is to average the pixels, and one is to sum the pixels. Well, in the case of this particular camera using raw 16-bit mode, binning is averaging. So basically what the camera is doing is it's taking 4 pixels and averaging the values together and then spitting out 1 pixel from that. So, which is a little bit different than maybe what other cameras do, and definitely different than what I've been used to using CCDs. But if you happen to use raw 8 mode, it actually sums the pixels. So I'm shooting in 16-bit mode, raw 16-bit, and that's what I'm seeing. You know, what happens is it's just averaging the pixels. So in essence, what it's doing is it's resizing your image, resampling it down to a smaller size, but leaving the same, you know, you're getting the same signal that you would do if you're shooting 1x1. And this is really interesting. And it has, it kind of tells to the sensitivity of these cameras. And I'm going to show this in a little bit further on down in the presentation. But this was one of those things that kind of got me a little bit, just, I was thinking, you know, something's got to be wrong here, but it's not. And if you're wondering, you know, before I get beat up on why is there a lot of vignetting over here and it's a little bit different on this one. Well, this actual flat that I'm showing here was taken using my reducer at f6, where there is a little bit of vignetting, and this is at f8 over here, was a little bit less. It's a little bit less light drop off. So anyways, moving on.
John, can you take a question before you move on? Because I see a couple of them have popped up over here.
Absolutely.
So, so John asks, what ADU range do you shoot for when you're imaging?
Okay.
And I mean, so I guess it's a little confusing. There's another question from Nori about what's the difference between imaging at 1 and binning at 2,
Okay.
because it kind of brings into question, you know, about resolution versus sensitivity. And if you're averaging, do you really get better image resolution, or are you just sacrificing image resolution by binning? I mean, there are a number of questions that come up from the data you just presented, right?
Yeah. Well, that's actually a easy question to answer. When you bin with this camera, you lose resolution. You're basically cutting your resolution in half, and you're getting a smaller file. That's basically all that's happening. Sensitivity doesn't change at all. You're basically...
So why do that? I mean, so
okay.
Usually you bin in order to get, let's say if you're doing colors, you're trying to get your color data more quickly, but if it's just averaging, what's the advantage here?
Well, the advantage is This camera has very small pixels, 3.76 microns. I am way oversampling one by one. Now, you may not be with a small refractor, a smaller, shorter focal length scope. But in my case, at 1200 millimeters, that gives me a sample resolution of 0.6 arc seconds per pixel, which is a little bit oversampled. I'd rather be around 0.8 to 1 arc second per pixel. So that's why I would bin, and that's what I'm going to kind of get into a little bit.
Well, I guess the next question will be, what's your seeing down there relative to your arc seconds per pixel?
Yeah, it typically averages around 2 arc seconds. I get some really good seeing at times to 1 arc second, but you know, the average is probably, there's no mountains around here, so it's around 1.5 to 2 arc seconds. Yeah. So, so that's that question. And what was the other one again? There was the first one you asked.
Let me see. What ADU range do you generally shoot for in an image?
Okay. Well, that all really depends on the brightness of the target or the brightness of the stars that are in your field. I shoot for a specific amount of time, and I'm going to get into that here pretty quick. I shoot for an exposure length that doesn't allow the light pollution to overwhelm the image, but long enough to reduce the read noise down to or to any other noise down to a very low level. So the ADU value that you end up getting in your image really just depends on the brightness of the sources that are in the image. You know, some are going to saturate and some probably won't. You know, a whole bunch won't, actually.
Well, I guess that's ultimately the question. Are you saturating too many stars?
Yeah.
Right?
Yeah, right. And I don't think so. And I've got some pictures to show you.
John, could I ask one more question as well?
Yeah, absolutely.
Yeah, this has to do, I've seen it come up in the stream where someone mentioned unity gain. Could you explain what that is for us CCD guys?
Oh, well, you know, I'm a newbie when it comes to CMOS. But unity gain, at least what I understand it is on CMOS cameras, is the gain that gives you the lowest read noise value. And I could be totally wrong, and you guys can shoot me, but I think that's what they mean. And I've seen that talked about a lot. In this camera, unity gain, I believe, is the gain 100 setting. But I could be wrong. And I'm going to profess that, you know, I know very little about a lot of the terminology with CMOS since I just started using it. But I think that's what that means.
I can explain it if you want.
Go ahead, Molly. Yeah.
So the way that so you have this light sensor, that's your camera, and when a photon hits it, it's going to create some number of electrons, some amount of charge in that pixel. And when you're at unity gain, one photon generates one electron. If you're at less than unity gain, it takes multiple photons to make one electron. And if you're at greater than unity gain, one photon creates multiple electrons. So unity gain is pretty much the, well, first of all, it's a balance between sensitivity and noise, kind of the sweet spot. But from an electronics perspective, it's ideal because it's sort of, think of it as oversampling or undersampling your photons as kind of a way you could think about it. But really, at the end of the day, it's a balance between sensitivity and noise.
Wonderful. Thank you for that explanation. I did not know that. So again, I'm a CCDer at heart, but however, with this camera, there's only 2 gain settings you need to worry about. Now you can change it to a whole bunch of other gains and so forth, but really the only thing you have to worry about is 0 or 100. 0 is the low gain setting. 100 is where the read noise drops off. And you know, I could there's a couple of slides, I believe, or a presentation on the ZWO and probably on the QHY website that kind of shows you where your read noise goes at different gain settings and so forth. And it kind of doesn't really change much, at least with this particular chip. You know, this is a newer technology back illuminated chip. So it's a little bit different maybe than some of the chips that have been out there in the past on CMOS cameras, like You know, I know the ASI 1600 camera is very popular. I don't know what chip is in that camera. However, I do hear people talking about unity gain here with that camera. So anyways, thanks, Molly. So I just wanted to show you guys, here's a 600 second master dark that I did. This was gain 100, bin 2x2. But really the reason why I'm showing you this is I wanted to show you how clean it was. I mean, there's some hot pixels here, here and there, but it's a very clean, you know, image. There's really nothing weird about it. And there's no big amp glow in one corner or another. It looks very similar to what I was used to using when it came to a CCD camera. So I did my first image with the camera in late July, early August. I shot Sharpless 112 in Cygnus. This was shot at f8, 1200 millimeters focal length. This was shot at gain 0. And I used 2x2 binning with this, really because I wanted 2 reasons. One, this camera produces huge images. It's 60 megapixels. I didn't want to have to buy a supercomputer to process the images. So shooting at 2x2 makes the file size quite a bit smaller. Instead of being 122 megabytes a sub exposure, it's about 31 or 32 megabytes. So this was kind of a test shot, and I shot at 2x2. I shot the narrowband part of it at gain 100, also 2x2, and this is a LRGB HA03 S combined. 4 hours of luminance, 3 hours of RGB, 9 hours of narrowband. And this was done from my backyard. So I was really impressed when I put this together. I mean, this was pretty awesome. I had actually shot this the year before with the STL, which was a 35 millimeter format camera also. And this thing kind of blew it away. Here's just another version of it, cropped and rotated a little bit. Really good signal. And I really got a lot of faint stuff. And I was really surprised about that. I was kind of thinking, man, I made the right decision. So I also did narrowband also at the same time with this whole first set. And this is what the narrowband image looks like. Just a typical SHO palette put together. 540 minutes for each channel. Very similar to what I was used to seeing when I was shooting with my fast reflector and refractors and so forth. But yeah, this was shot at f8. Oh, here's one more. This is an image I just recently did at the El Dorado Star Party in October. And this kind of was interesting in its own way because at a dark site, I typically go for 5 to 10 minute sub exposures. Well, my sub exposure calculator said, nah, you're going to be shooting at f6 at a star party, dark sky. You don't need to shoot more than about 95 seconds. So these were 95-second luminance sub exposures and 90 minutes of those, and roughly between 110 to 120 minutes of RGB exposures with 150-second sub exposures. Because, you know, if you're using filters, you don't get quite as much signal through the filters like you do with luminance. So, and I was floored when I put this together. I was like, okay, this is really cool. This is a really nice camera. I can shoot very, very short sub exposures, and I can get really good data that's very low noise. And the last one I just recently put together here, this is a little tiny planetary, about 1 to 2 arc minutes in size, a Bell 78. And I shot this at 2x2, but I tried something different with this one. I drizzled it up to the full resolution of the camera. So this, what you're seeing is what about full resolution would look like if I had shot it 1x1. And this is a crop of a tiny little section of the chip. This isn't the whole chip by any means. There was like 35,000 stars in the chip, and then this one little tiny planetary. So I cropped it just to kind of show you what the planetary was. And I did do this one at gain 100 all the way around. So there are plenty of colorful stars here. If people are thinking, man, if you shoot gain 100, you're going to blow out your images. Not true, at least not in this case. Okay, here's a little comparison, and I'm going to start trucking along here because I'm probably going to run out of time here pretty soon. This is the difference between the ASI6200 on the left and the STL on the right. The big deal here is you may look at those and say, they look about the same. Well, the STL image was taken 2x2 binning, and it has 9 micron pixels at 1x1. So these are 18 micron pixels, and I shot it at f6. The scope is at f6, a little faster speed, and the QE of this was only 31%. The ASI image was shot at f8 using the same 1200 second sub exposures, and I don't know if you can see it as well as I can, but I can see the faintness, the stuff that's faint in the background is a lot more defined in the CMOS camera as it is in the CCD camera. And a lot of that probably has to do with read noise and quantum efficiency. I mean, this IMX455 is a very high quantum efficiency chip. Here's another example of a recent image I did of Barnard's Galaxy. Over on the right is, I had also shot this last year with the STL. This was a 338 second exposure. On the left is the ASI camera with a 300 second exposure, gain 0. Down here on the bottom, on the number of stars, 11,300 stars on the ASI shot. On the STL shot, 10,611. And, you know, I'm assuming, yeah, there may be a slight difference in, you know, sky, but the galaxy is brighter. There's more faint stuff visible in the CMOS camera. I mean, this little thing here is the bubble nebula within Barnard's Galaxy, and you can actually see the bubble here. And it's really hard. I mean, since I know it's there, there's a little bit faint outline of it, but things are a lot brighter. So, and before I get yelled at, well, you're shooting 2x2. I got to remind you that 2x2 is just averaging. So you're really seeing the inherent sensitivity of a 1x1 image. You're just seeing it packaged in a smaller size when you average those 4 pixels together. So yeah, I was really happy about that. It's definitely more sensitive and definitely less noisy. Now this is a little animation, and I hope you guys can see this. Between the STL and the ASI camera using Barnard's Galaxy here, you can see it. The brighter one is the ASI camera. The little fainter one is the STL, and it's a longer exposure using a much bigger pixel, 18 microns, that you'd think would intercept a whole lot more electrons. But you know, it's older technology. Kind of interesting. Okay, so let's compare this to some other chips that are out there on the market. The IMX455 has very small pixels, 3.76 microns. Really good QE, almost up to 90%. And that's not the whole chip, but on average, you're probably going to see about 70 to 75% QE. It peaks in the green. Read noise, 1.6 to 3.6 electrons, very low dark current, and very decent full well capacity, 50,000 electrons. The very popular KF16200, you know, a little bit bigger pixel, maybe a little bit better match for some telescopes. QE 60% on average. Read noise is advertised to be 6 to 8 electrons. But my guess is that many of you, if some of you are using this chip, you may have a little bit more than that. Dark current, not too bad, and pretty good full well capacity, 40,000 electrons. The ever popular 8300 chip that's in a lot of cameras. Close to 6 micron pixels, 56% QE. Read noise 9 to 11. My camera had more than that. My camera had almost 15 electrons of read noise. Pretty good dark current, and full well capacity 29,657. And then the 16803, very popular. It has bigger pixels. Maybe it works better on larger scopes. It's more, you know, it fits the those scopes much better. Pretty good QE, very good full well capacity, over 100,000 electrons. Dark current's not too bad, and not too bad in the read noise. But you know what I used to think not too bad is really not too bad. but this is really good. Surprised the heck out of me, really good. So this camera has excellent QE, really low read noise, really low dark current, and really good well depth. So if you guys haven't seen this before, hopefully if you look at this later, maybe on the YouTube recording, the guy that developed SharpCap, Dr. Robin Glover, has a really good calculator when it comes to figuring out what your exposure time should be. And he has a really neat calculator online that computes your sky electron rate. And the calculator takes into account things like sky electron rate, your QE, your filters, your bandwidth, and so forth. And you can figure out an exposure time of what you should shoot from your sky using your light pollution. Well, down here at the bottom are the numbers that I got using my older QSI 683 and the new ASI 6200. So I used to shoot for this 5% noise level, which is pretty standard. It would take me 344 seconds at f8, using the scope I have to reach that. And I like to go lower. And recently, before I quit using that camera, I was shooting 800-second luminance exposures from home. So this calculator said, yeah, 862 seconds for a 2% noise level. Well, for the ASI 6200, 80 seconds for the 5% level, 200 seconds for the 2% level. So it's a whole order of magnitude better. I mean, I'm shooting exposures now, typically, since I'm doing gain 100, at about 120 seconds, and I'm getting everything that I ever used to get in 5 to 10 minute exposures with a CCD. So pretty cool stuff. So if you haven't seen this, check out these two links. Calculate your own exposure time that you should use from your sky at home, and I bet you'll be surprised that maybe you've already done this, and maybe you're shooting as long as you should be. So I thought I'd throw that out there just to kind of give you guys the difference between the two cameras. So what have I learned in the last 4 months? Well, this camera acts a lot like a CCD camera. I mean, I wasn't surprised really at all, except with the flats. I had to figure that out. What is it really doing? And it's averaging. So at least I understand that now. Cooling works really well. It cools down to 35 degrees below ambient. But you got to remember, most CMOS cameras nowadays don't need to be cooled as much as maybe some of the older technology CCDs to get very low read noise. I'm sorry, very low thermal noise. The read noise is already really low. I haven't had any weird calibration issues. Haven't had any problems with dew on the cover slip, although the camera does have a heater that's built in. I haven't had to turn it on, and I live in an area where it's 80 to 90% humidity all the time, and it's been just fine. Interesting, shooting 2x2, especially with this camera, and it may be different with other ones, but with this one, it doesn't really increase your sensitivity at all. Really, all you're doing is making your file size smaller and resampling your image. So I see it as a way that I can fit it to more than one type of scope. If I'm using a short focal length refractor, maybe I would shoot 1x1. A long focal length refractor or a reflector, I would bin it. I'm getting the same native sensitivity no matter which mode I use. So, yeah. It downloads really fast, just a few seconds. Now, they say it's backwards compatible with USB 2, but I'm not so sure because I tried it. It did not work very well at all. I got some funky lines in the image. With just using the native USB 3 connection, it works just perfectly fine. I have seen maybe some memory issues using the SkyX. You got to remember, this is a huge chip. This is 60 megapixels, 133 megabytes per image. And I had some memory issues when I ran an automation run one night using the SkyX through CCD Autopilot. And I've seen some other stuff written about this on the Software Abyss forum. And it may boil down to, and I'm not totally 100% sure, but it may boil down to that the SkyX being 32-bit in the way it packages everything in the program. Your FITS viewer is in there, your camera control, everything is in there. So it's got to manage memory really well. And yeah, I ran out of memory one night using it. So what I've been using lately is Voyager, and Voyager has works wonderful for automation, and it has a separate fit viewer from the main program. So the fit viewer is 64-bit, the main program is 32-bit, and they're totally separate programs. And tends to work fine. I have no issues at all. So some pros and cons. You know, I don't know. You know, pros for sure: excellent QE, low read noise, good well depth, really fast download speeds. I didn't mention this. You can utilize ROI. So if I used it on a scope that couldn't handle a whole 35mm chip, well, I could pick a region of the chip that I knew the correction was good and just image there. And you can do that with a lot of cameras. It's high resolution for sure, and it'll test your optics. It's a good match for medium focal length scopes. Long focal length, you may want to use binning. And my opinion is the performance to cost ratio for this thing is pretty darn good compared to CCD. You know, when you look at the cost of buying a brand new 16200 CCD type camera, or a brand new 16803, or, you know, maybe a different version, even the 8300 chip CCD camera, you're going to spend what, $3,000 to $6,000, $7,000, $8,000 when you talk about the camera, the filters, the filter wheel, the whole works. Well, this thing is pretty darn, you know, pretty good in that respect. You know, the camera's around $4,000, maybe a little bit more for the QHY camera because it has a few more features. But you know, I think what I would call the performance to cost ratio is pretty darn good. Some cons, yeah, small pixels. You got to kind of pick your poison here, I guess. The read noise does double, and I didn't go into this. The read noise doubles with binning, and that's because you read out all 4 pixels, it combines all in software, and then you take the square root of the read noise, and you get the end result. So the way CCD works is it bins in hardware, reads out all those 4 pixels one time. So it's 1 shot of read noise versus 4. But the read noise is so low that it's really not really a big impact. It has a huge file size if you shoot 1 by 1, 133 megabytes. Easily, one night I shot 1 by 1. I got 8 gigabytes worth of data in that one night, and I would shoot over multiple nights. So yeah, it's a lot. You need a pretty fast computer to process those images in the 1 by 1 file size. A lot of good cores. You need a lot of storage, and yeah, maybe this is a con, maybe it's not, but the binning really doesn't increase the sensitivity. So at the end here, you know, CCDs produce great images. They've worked wonders for me. CMOS cameras produce great images. CMOS technology has really come a long way. You can bet that Amplo is a thing of the past, especially with the new generation back illuminated chips. And there's other ones out there from these 2 manufacturers that are back illuminated, smaller, maybe a little less expensive, but they advertise 0 Amplo, and I believe them because this one doesn't have any Amplo at all, 0. So my opinion, so yell at me about this, not anybody else, but I think these new generation back illuminated chips, you know, they've reached CCD performance and surpassing CCD performance in many areas, especially read noise and quantum efficiency, at least in the case of this particular chip. And I know I've seen some of the ads from the latest cameras coming from QHY and ZWO with, and I don't have the numbers of what chips they are, but they advertise really, really high QE again and no Amplo. And these are back illuminated chips. So, but is this better than a CCD? I don't know. This is kind of subjective. I guess it depends on what you think is better. I use both types of cameras, and they both produce wonderful images. I do love the performance of this camera, though. I mean, it's really, really cool. But in the end, this is all good news for all of us. So thank you so much. Here's my contacts on there if you guys want to get a hold of me. And yeah, so I will leave it at that. And we'll go from there.
You've actually stimulated a ton of discussion about CMOS cameras. It looks like we have a whole bunch of people watching that have CMOS cameras and are sharing their experiences relative to what you're presenting.
Yeah.
Not being a CMOS user, it kind of leaves me in the dust. Lee did ask, what's the longest sub-exposure you've been able to do without saturating stars?
Oh, well, I can saturate, if I shoot at a bright enough star, I can do it in less than 60 seconds. I can probably do it in 30 seconds at Betelgeuse, I mean, that's all relative. It just depends. My typical sub exposure, though, is 120 seconds at gain 100 and about 300 seconds at 0. So, when I was shooting with CCD, I would get saturated stars when I was shooting 600-second sub exposures. I mean, sometimes they were there. I mean, yeah, it's all about testing. Depends on your optics, depends on your the speed you're shooting at, your particular chip, your camera. There's a lot of stuff that goes into that. So there really isn't a defined answer, I guess.
Now, can you bin more than 2x2?
Yes, you can. You can, I believe, go up to 4x4 binning with this camera.
So you could get color information on a star field really quickly.
Very quickly. I've been shooting 2x2, and still it's blowing me away how short my exposures need to be, and what I can produce when it comes to background noise. Very short exposures. Now, my total imaging time is still a lot. I shoot 15, 20 hours total, but that's just what I do. That's maybe it's my old CCD habits still out there.
Does that camera have a shutter?
No, it does not. It has what they call a rolling shutter.
That was one of my questions about your total time, John, compared to CCD. I'm used to doing very long exposures. And it sounds like you're doing the same thing. You're shooting 20 hours.
Yeah, and I'm doing that because that's all I know right now from home. Now, I did show that one image of the Bernard 204 area I shot at the El Dorado Star Party. That was not very long. That was about maybe 6 hours of total exposure time. I mean, I did like an hour and a half or so luminance, and then, an hour and a half maybe of each color or something. And it was wonderful, but it was a really dark sky. That was a true dark sky. From home, to beat the light pollution, I'm just used to shooting a long, long time to equal what I could do at a dark site.
And I suppose that you really have to match your decision on binning on what your seeing conditions are, because you don't want, if your seeing conditions should be about half of your arc seconds per pixel.
Yeah, for me, it's been a pretty easy deal, though.
I'm sorry, it's the other way around. You're seeing your arc seconds per pixel should be about half of your seeing. So that will make a decision on whether you bin or not.
Yeah.
Right?
To a third. Right. So typically I'm typically probably 2 to 3 arc seconds. There are some nights, I'm way south. I'm along the Gulf Coast, and there's no mountains. I get some wonderful seeing at times. But once I'm set up on an image, I'm not going to change it from one night to the next. So I just decided that I like to be around 1 arc second per pixel. And if I change the scope to f6, then I'll shoot maybe one by one, because I'm at about 0.8 arc seconds. And that gets me about, a third gives me about a seeing of about 2.5 to 3 arc seconds. Yeah. So.
Yeah. And of course, everyone's saying excellent presentation, which we appreciate. Did you attend the meeting out at San Jose on just this issue in 2019? You remember there was a long discussion and a lot of back and forth about CMOS at that time.
Yeah, I didn't catch that particular session. I was actually out there working for a vendor, so I had to pick and choose which sessions I went to. But I remember seeing the QHY presentation of the unveiling of their new camera. which is why I brought that up. But no, I didn't catch that session. I'm sorry I didn't, but and to be honest with you guys, I'm a newbie when it comes to the CMOS stuff. I mean, but I'm not a newbie when it comes to just imaging in general. So I was really, I'm just overly impressed with this darn camera. If you have a box that can handle a 35 millimeter chip, this will blow you away when it comes to what it produces. It's pretty cool. And and I'm not going to argue that ZWO's camera is better than QHY's camera. I mean, they both use the same chip. They use similar technologies. Some have different. The QHY has slightly different features. I haven't used one, but my guess is the performance is about the same and probably just as good, or mine is just about as good as the QHY. Yeah.
John, do you reuse your darks? Do you build a dark library like CCD?
Yes. So I have a dark library. The one difference and this is something I had read about and I've heard a lot. The only thing I do different with this when it comes to the dark stuff is I take flat darks and I apply flat darks to the flats. With the CCD, I could just have a master dark, a master bias, and I could optimize those darks and scale them to anything I wanted to. I haven't tried that yet with this. I'm going to, and I bet you it's going to work okay. But to be on the safe side, since I've only had it for about 4 months, I've been using, just a typical dark library that I built. And when I calibrate the flats, and I do this in PixInsight, I just use flat darks, and I have a master flat dark. And I've used the same ones now for 4 months, and they're working fine. So I guess that answers your question. I don't take darks every time I image, so I have a library.
Yep. That's all after. Thank you.
Yeah.
Alex, do you have any questions?
Well, just a couple of comments. One of the slides had a comparison of the CCD chip next to the CMOS chip, the results of it, and I noticed the column defects, and didn't notice them in the CCD chip because they don't have the columns and stuff. So
that was actually the other way around.
Was it?
Right, that had the column defects. That was the STL11 CCD camera.
That's right.
Yeah. So basically, I don't think those were column defects. I had an older dark library when I calibrated that image, and I probably should have. That chip, you had to take new darks probably once every 6 months. Things change.
Well, I'm thinking a CMOS chip would not have a bad column, would it? I mean,
that's right. Yeah, because instead of reading off by row or by column, CMOS chips are there's an amplifier behind each pixel instead.
Right.
Yeah,
yeah.
Exactly.
So you're not going to see those like column or row defects. So just have individual hot pixels.
Right.
And Jeff, could you go back to the page with your email on it, or could you recite your email? Jeff Weiss wanted to know. I mean, John, could you?
Oh, I'm sorry.
For Jeff. Yes, okay. I'm sorry.
Okay, so let me go back to my and there we go. There we go. Can you see that?
Oh, let's see. Good. There we go. Yeah, I can see it. So it's there.
I think the somebody else commented in the chat that it was too small to read on the YouTube stream.
Okay. Well,
so if you don't mind, I can put it in the chat.
Sure. Yeah.
Okay.
Yeah, you can put any of those contacts in the chat there. That's fine.
Eric, have you had a chance to go through and make sure we got all the comments you've asked?
Yeah,
one way or the
there
other?
was mostly a discussion, but I have another comment.
Go
I
ahead.
think somebody has to stick up for CCD during this discussion. So
Do we have anybody old enough to do that around here?
yeah, I'm definitely old
Okay.
enough to do that. So I guess my only comment would be when your comparison, the STL camera with the 11,000 chip is perhaps an older generation of CCD chip as compared to something, let's say like the 16200. And it would be nice to see that same kind of analysis. Obviously the CMOS would come out better in some ways, but the 16200 might be a better more contemporary CCD comparison of
Well,
the
yeah,
two.
And after tonight's presentation, you should be able to pick up a 16200 pretty cheap.
Oh, don't say that. I have two of them.
Yeah. No, I agree wholeheartedly with you. I just don't have one of those. I used what I had. I can tell you, however, though, it's a heck of a lot more sensitive than my 8300 base sensor too, which was the 683. But yeah, I don't have a 16200. But looking at the specs, I mean, the QE of the 16200 is around 60%. The QE of the 8300 is around 56%. So there's a little bit of a jump and a little bit less read noise. So, but yeah, no, you're right. I'd love to see a comparison between those two. And like I said, CCDs are great cameras. CMOS, I was very skeptical for a long time. I had an argument with a guy over CMOS one time saying it'll never be there. But, using one for 4 months, at least this particular one, has changed my mind on where I think they are in the technology side of the house,
Yeah, and I think I remember at AIC, I think there were a couple of fist fights that actually broke out. People discussing CCD versus CMOS.
Yeah.
And yeah, I guess the other comment I would make is that, we're all prisoners of the seeing conditions wherever we image.
Absolutely.
And it would be nice to get the theoretical limits of the camera, which we almost never do. So I just wonder how much the camera makes a difference and how much the seeing conditions really are the ultimate control of what you get out of an image. And again, ultimately, I think we'll all go to CMOS, but when do we jump?
I think you're right. But what you get out of the image really is controlled by the resolution of your system, as a whole, because you have a certain size pixel and you have a certain focal length, and you can only get so much out of it. So a lot of it has to do with how well you are when it comes to processing stuff. But yeah, I'm really excited to maybe try the ROI feature of this camera and shoot some planetary stuff at full resolution or with a Barlow, just at a fast frame rate, but just a little tiny section to see what I can do with it there too.
Do you know what kind of frame rate you can get if you crop that down to say 600 by 600 or some?
I think it's around 50 frames per second if you have a small enough crop. 50 frames per second. At full frame, it's only 2 frames per second. So, but with a little crop area, I think it's about 50. Is what I read.
As an anecdote, I've on my 1600 when I cropped it to something like 320 by 240, like a real tiny crop, I have pulled as high as 199 frames per second.
Awesome.
Yeah, and I can say I have a 533 ZWO, and when you crop it down to 600 by 800, I get around 100 frames. So I think you could probably zip right along, especially with a USB 3.
Yes.
I bet you could get over 100 frames per second. And it might be a really cool planetary scope with all those pixels.
Yeah, it could be. It's just that I haven't, had a chance yet to try it. So still kind of new.
John, we have a question from John. Molly's answered it, but I'd like to hear your opinion too. CCDs deteriorate over time, the hot pixels and dead pixels and stuff like that. Do CMOS do that?
How about we come back in about 2 or 3 years and I can answer that.
I think the answer is that they all do.
Yeah,
One of the key things is that the way a CCD reads out the information means that it may take out a column at a time. Now, believe me, people have been dealing with this for years, and it's easy enough to cosmetically correct around it and stuff like that. But I think you would lose a pixel at a time in a CMOS camera. I also wanted to point out that our friend Richard Wright did a presentation, you referred to it 4 or 5 months ago, where he said that there's no question that CMOS is making great strides. However, he, in his opinion, thought that it had not quite caught up yet. I wonder how I have to ask him to find out if and when it catches up and things like that. So,
well, I can maybe sort of answer that, because him and I had a really good discussion the other day on the phone. He's a good friend of mine, and he's going to start using this camera with a couple friends of his here very quickly. So maybe he'll come back and do another presentation after he uses the 6200 to give a little update. And I'm going to be imaging with him next month, so he'll get to see mine, and we'll have a nice discussion. But yeah, they've come a long way for sure.
Actually, Larry just popped up with another question.
Yeah.
How do you do your darks? Do you cover the scope? I mean, it has no shutter, right?
Yeah, no, you just put the lens cap on the scope, and that's it.
That'll be a bit hard if you have a remote observatory. You have to come up with an alternate solution.
Yeah, you'd have to have maybe a one of those automated flat
flaps.
Flat. Yeah. Yeah.
Larry, I use a dark filter. It's basically a piece of material, opaque material, cut to the 2-inch, and it fits right in my filter wheel, just like every other filter. And I always take my darks with the observatory lights off. I don't take them during the day with the bright light around and stuff like that. And if you want to see how all that works, I mean, you're all of 3 observatories away from me out at the go. So it's possible to do. And have we got all the questions, Eric?
I think so. I'm still watching. I don't.
Yeah.
But there's a ton of discussion about this. I mean, that everyone is arm wrestling about this.
I have been torturing a CMOS camera out from my all-sky camera, and it's been in place for a few years. And when I compare it now to when I first installed the camera, there's a terrific amount of hot pixels. So the pixels are stuck on. So you see the green pixels, the red pixels, they're just stuck on now. So yes, they do deteriorate.
Is there any issue with processing in PixInsight that's aside from file size, which is noticeably different?
No, it's exactly the same way. I've noticed no difference at all. Other than, like I said, I use flat darks to calibrate the flats. Basically, it's the exact same processing flow.
Okay, I'm gonna start wrapping this up. Eric and Molly and Terry, if you could scan to make sure we've got all the questions. Everybody, if they bothered to question, ask us the question. Let's make sure we can get them in there. Jeff asked if these comments stay while he watches. Yes, the comments stay along with the program as they forever. They're still you can always read them later.
Yeah, and then the chat will play in real time with the video.
Yes.
So as you watch the video, the comments will come in as if it were live. But it takes a few hours for the video to process after we go live, so those won't be available right after the video. But if you watch it tomorrow, then the comments will be there.
Okay, Anak Chand left us, and because he had to go someplace else, and he wanted to thank the AIC folks. We have to be careful here, guys. AIC means the Advanced Imaging Conference. We're TAIC, the Astro Imaging Channel. And we have good friends at AIC. And I don't know why we picked that particular name. I mean, Astro Imaging C, whatever it is. But there is some confusion. We are not AIC. AIC is another bunch of really good people. And we got some really good news from them. We got an email that went out about 3 or 4 weeks ago now that said there will be an AIC. They're gonna open up San Jose again. that there is a future in our lives. Things will settle out. And AIC is coming, what was it, the first or second weekend of October? So, start looking up AIC. That's where they got some really, 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 really good discussions going on. And so try to be part of that. Okay, everybody? Crew, do we have anything else we've got to say in here?
There was a question from Anak Chan on how to contact Terry. I think something that Terry said he wanted to follow up on or something like that. Terry, is there a good way to contact you?
If nothing else, he can write to us and we will.
Terry left the meeting. I guess he didn't want to be contacted. Just kidding. Anak, we'll ask again next week.
Anak, will you? Well, you're not here
Terry's
anymore. You said goodbye. If you could,
That's
contact us.
mouse hand coordination. Sorry.
What is actually happening here? Oh no.
Okay, Molly, settle.
Okay. If you need to get a hold of us, folks, by the way, some of you folks put comments on the YouTube afterwards. And I don't think there's any of us on the TAIC group who actually read those comments and respond to them on a regular basis. So if you want to know something about that, the better way to contact us is by going to the astroimagingchannel.org. Okay. And you've seen me do it a bunch of times now. Let me share my screen just to make sure. Present my entire screen. Boink, share. And there's Molly. And there we go. If you just go to contact, if you really want to contact us and ask something about the show, this is the place to do it. We just don't, we don't follow all the other different places as tightly as we do here. This actually generates an email to us. Okay? So that's the best way to do that. Okay, where are we in this? Is it about time to wrap it up?
I think it is.
It's that time.
Okay.
Okay. Molly into the happy sauce.
Yeah,
twang
the magic twanger front.
Fine, okay. This is just my personality. Thank you.
Molly, I think you're in charge now. So
all right, I was going to do one last question on YouTube.
Oh, do we?
I think we're good to go. All right, good night, everybody.
See you next week, everybody. We're going to Mars on the ISS. Not really, but
hey, John,
that's an idea.
Hang out with us a little bit when we
no problem.
off here.